Okay, so the second part in this lecture series is going to focus on calculus, right? So most people, if not everybody, following this lecture will have some grasp of calculus that they've done leaving cert or high school or whatever. But just to like refresh ourselves on what we mean by some terms, we're going to go through the basics of it and some of the rules and techniques of differential and integral calculus. So the first idea is limits. So the limit is the bedrock of calculus and how calculus was formed originally. So the idea is if you have a limit, say of a function, we can write it as, let's say the limit as of f of x, so a function of x, as x tends to some number a. This means that not how we evaluate f at the point x equal to a, but how it leads up to it. So if we have, say, some graph, let's say here, where the function, it looks quite normal, but at a certain point here, it's not defined. That we say a. Now, if we evaluate this function f at the point a, it'll spit out some undefined, something undefined. But if we if we have a look at the limit as x tends to a, so from the left, how it's like moving up in this direction, and how it's moving down here from the right, and if they both agree, so the limit from the left and the limit from the right, that f of x evaluated at a almost reaches something that it kind of tends towards a certain value, then we can define that value, we'll call it L, as the limit. So most of the kind of calculations to do with that, with evaluating from the left and from the right, they don't really matter, but the idea is crucial, because it allows us to deal with zeros and infinities in a way that we might not otherwise be able to. So the idea of differential calculus, geometrically, is taking graph or taking tangents to a curve. So we have, let's say we have a graph of, let's say x squared. So it looks something like this, right? So we have f of x equal to x squared. Now we want to find slopes. We're dealing with slopes. Let's say we can say at x, we can say how this is x and equal to a and b here, and we can get a slope here. This is fine. We can say the slope here. So the slope is the change in y over the change in x, which in this case, that's fine. We just say f evaluated at b minus f evaluated at a over b minus a. And this is the geometric way of thinking about slopes that we've come across tens, if not hundreds of times before, and there's no problem. The only kind of, not issue as so much as just thought, that we can kind of toy around with is the idea that if we move these 2 points closer and closer together, we'll still be able to have a slope here, that's fine, here. But then what if we want to deal with it just at one single point? And at that single point, the slope looks like the tangent line to a curve. So the tangent, you might remember from dealing with circles. If we have a circle like this, the tangent line is the line that just tips off of it, like so. So we need to apply the same premise to a curve and find this line here, this bottom line, that just tips off the curve at exactly 1 point. How would we find the slope of that line? So we could say by moving B and A infinitely closer, or infinitely close together, so that the distance between them is infinitesimally small. we could find, in theory, this slope. But, I mean, from a normal or intuitive mathematical idea or sense, that makes no sense, right? There's no, we can't have this change in x being 0, because then it would blow up. So that's where we use our limits, our idea of limits. So we can rewrite, let's say we want to find the slope here, right? So we can say, instead of delta y, we'll use delta f. So this is going to be the change. So we'll say this is f evaluated at, let's say, some point t plus delta t. This delta t is some, so we were say, let's have it at, say, this point t here. And then some delta t could be, moved up a little bit. So that's here, t plus some delta t. Some number, it doesn't really matter. And we subtract then f of t off of this. And that gives us our change. So to find our slope, like we have our dy over dx, or delta y over delta x here, we're going to over delta t, which is our changing variable here. So we can rewrite this then as all of this over delta t. And this, if you've come across the differential calculus or derivatives before, is starting to look a little bit familiar. So now we have an idea of how to calculate the slope at a certain point, t. We're going to have to use our limits now, because as great as this is, it doesn't give us exactly pinpoint where we want to go. So we now have to take a limit, and we'll, instead of using delta f and delta t, now we write df dt to show that it's now a derivative. It's now the limit being taken instead of some normal amount. So we then write this as the limit as delta t approaches 0. So this number here approaches 0, and the difference here squeezes into nothing of f of t plus delta t minus f of t over delta t. Right. So now we have an idea. We have our derivative defined, okay? This is key. So key. I'm going to put it in a box. Right. This is really the takeaway. This is how we define the derivative, a central idea to everything we'll really be doing. So now if we were to take f of x and fit this in, say up here, we have df dt. Well, we'll instead of calling it x, actually, to keep things tidy, we can call this f of t. So from some general point t, we say this is the limit as delta t goes to 0 of, so if f of t is t squared, we put t plus delta t in, t plus some delta t squared minus t squared over delta t. We can evaluate this out. We'll get the limit as delta t goes to 0 of t squared plus 2t delta t plus delta t squared minus t squared all over delta t. Right. So we see that this t squared here cancels this minus t squared here, and we can start dividing things. So we'll have the limit as delta t goes to 0 of 2t times delta t over delta t is 2t plus delta t squared over delta t is just delta t. And then as delta t goes to 0, this first part is going to be unaffected, and this second part goes to 0. So we find that df dt is 2t. Right, so that's an example of calculating a derivative from first principles. Something that you probably have come across before, but this can get very tedious very quickly when you have very complicated functions, so you won't really deal with it at all. So mathematicians in the past have, instead of dealing with all this, have created kind of tricks to do it instead. So that's what we'll be going on to next. Okay, so there are a few main techniques and rules that we can use to evaluate derivatives without having to go through that whole mess of first principles. But before we go on to those, there's a slight notation difference. So I just want to make sure that if we have some function f of t, and we want to take its derivative, there are three main ways that we can kind of show that. So we can say df dt, which is how we did it before. We can say f prime of t, or we can say f dot. Now this dot one, the last one, is Newton's old notation for it, and it's pretty much only used for time derivatives. It's reserved for taking the derivative of a function with respect to time. So we're not really going to use that right now, but we will use it a lot in the future. So there are a few rules. The first of which is called the power rule, which takes precedent when we have a function being some t to the n. And the way that we take its derivative is, well, let's try evaluating it from first principles. So we have f of t plus delta t, which is the same as saying t plus delta t to the n, minus f of t, which is t to the n, over delta t. Now, evaluating this t plus delta t to the n, we have to use something called binomial theorem, which is one of Newton's discoveries, where we can write t plus delta t to the n is the same as the sum from k equals 0 to n of n choose k times t to the k times delta t to the n minus k. So this is Newton's binomial theorem, which we'll use to evaluate this part here. This whole block of notation isn't too nice to look at, isn't necessary to deal with. But if we start taking terms out of it, we can see how they're useful in taking this derivative. So when we have the limit, so the t goes to 0, and the first term will be t to the n plus n times t to the n minus 1, and then we'll get some functions, but all using, delta t times t to the n minus 1 plus delta t. And then the rest of them will all be delta t to some squared or some higher power, but we don't need to worry about that. Minus t to the n, which is from up here, all over delta t. So these two will cancel, this t to the n, this t to the n, and this delta t here will cancel with this one on the bottom. But note that all the other terms that we get from this, from Newton's binomial theorem, will all stick with a delta t somewhere, even after they're being divided by delta t. So we'll end up with the limit as delta t goes to 0 of n times t to the n minus 1 plus delta t times some function. That doesn't really matter. But we'll notice that as delta t goes to 0, all of these will go to 0. So we're left with f prime of t as n times t to the n minus 1, which is something that you might have seen before doing derivatives normally, but now we know exactly where it comes from, and we can have complete faith in its rigor. So that's what we call the power rule, and we can add that to our rules and techniques. Okay, so this is quite useful for dealing with functions that are of some power, right? We'll keep that in our head, and we'll see how useful it can be later. The second technique is dealing with sums. So if we have some f of t here. Okay. We'll just draw a new box. Some f of t, which is the sum, we'll say, over n of some constant times t to the n, right? So what this means is, so from, let's say, n equals 0 to infinity. What this means, it's an infinite series, and if you haven't seen it before, it's not a big issue. And you will see it, but you will see it again. What this means is we have different constants out front, in front of our t. So we can start talking about this as some constant c naught, which can be 0, 1, 2, 3, or any number at all, any real number at all, times t to the 0. Please remember our first term to sum is n equals 0, so c0 t to the 0 plus c1 t plus c2 t squared plus blah 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 to some cn t to the n and then on to infinity. And what this basically means is it's any polynomial, anything that you can represent as a constant times t to the power n. So this is all that means, is that it's some polynomial of however length, we don't really care. So then we have to calculate its derivative again. So now we have our function t, or f of t. We can say that the derivative is the limit as delta t goes to 0 of the sum of cn times t plus delta t to the n minus the sum of cn times t to the n. Both of these sums from n equals 0 to infinity, n equals 0 to infinity, over delta t. Now, when we're dealing with sums, we can often combine them in certain ways. One of the ways that we can do this is we can combine these two sums together quite easily, right? Because if we're taking some sequence and we're adding it together, we can add it together with another sequence. So because these two sums are the same, we can take them out. And we can also factor out this cn here. So now we have the limit as delta t goes to 0 of the sum of c to the n times t plus delta t to the n minus t to the n over delta t. Right, and this part is starting to look a lot more like what we had before, right? There is a way that we can interchange this limit and sum. We can interchange a lot of different operators like that in calculus and so on. Sums and limits or derivatives, and it has to do with functions being well defined throughout their domain. But we'll assume that f of t is well defined for all real numbers, so we don't have to worry about any issues that might deal with. So we can swap these. So then we'll have the sum of, and another thing that we need to mention is that because constants are constant, they have no impact on the function, or they have no reliance on t at all, we can take them out of the derivative. We can kind of see that back here, that if we had some constant here and some constant out front, we could group them, factorize them, and because they're not affected by delta t, we can bring them out of the limit. They're not affected. So by using this, we can write c to the n times the limit as delta t goes to 0 of t plus delta t to the n minus t to the n over delta t, which we'll recognize from our power rule is just going to be the sum from n equals 0 to infinity of c to the n times t to the n minus 1. So this proves here that your sum doesn't actually matter. So if you take let's say some ax squared plus bx plus c, we can evaluate that as a whole. So the derivative of ax squared plus bx plus c, or we can take that as the derivative of ax squared plus the derivative of bx plus the derivative of c, and that will be the same. The sum here doesn't matter. So we can use that, we can call that the sum rule. Right. Okay, so the next rule we're going over is called the product rule. It's when you have a function, let's say f of t, that is composed of two other functions, say g of t times h of t, this applies. So again, we'll start off with doing it from first principles. So if we have f prime of t, it's the same thing as the limit as delta t goes to 0 of g of t plus t times h of t plus delta t minus g of t times h of t over delta t. And we can rewrite this in a way. So if we have g of t plus delta t times h of t plus delta t, we can add and subtract g of t plus delta t, h of t. So this term here, this last term, we're going to add and subtract it at the same time, which is a common trick used in limit taking and that type of thing, because it evaluates to 0, and so we're not changing anything about the function that we have, we're just manipulating it in a certain way. And by doing this, we can then group terms together. So we can group g of t plus delta t here and here, and we can factorize that so that we get h of t plus delta t minus h of t from here over delta t plus, and we can split this up again, we'll get g of t, h of t times g of t plus delta t minus g of t from back there. So g of t plus delta t minus g of t all over delta t. And then we'll see when we take this limit, this part here, this g of t, will go to g of t, because this delta t will go to 0. This part here, this term, will go to h prime of t. This part here will stay with h of t. And this part here will go to g prime of t. So we can write this instead as, we say f prime here is equal to g times h prime, g of t times h prime of t plus h of t times g prime of t. And this is called our product rule. It's quite useful in evaluating different derivatives that have anything to do with a product, and when combined, we can get a pretty far-reaching understanding of how different derivatives work. The last, or second to last, of the derivative rules is called the quotient rule. We won't go over the derivation of that here, but it's not too difficult, can be thought out as well. It's really kind of a, how to say, a special case of the product rule. So in the case where instead of having f of t instead of having f of t equal to some g of t times h of t, which is what we have with the product rule, we'll have some g of t divided by some h of t. And so this would lead to f prime of t being, v du h prime of t over h prime of, or ht squared. It's kind of messy. It's in the notes and it's quietly available online, but it's another rule that we can use. But again, it's pretty much a special case of the power rule, because if you were to replace this here with 1 over h of t and evaluate the derivative, it will be the same thing. Okay, so the final of the derivative rules that we'll go over, it's probably the most important in single variable calculus, multivariable calculus. It's very kind of key to understand this, is called the chain rule. So it's really useful when we're dealing with composite functions. So when we have, say, f of g of t, for instance, or so an example of that might be the cosine of the sine of t, right? So when we're dealing with this, it might seem, you know, kind of weird to look at, or might seem weird that, you know, it's quite important, because, you know, when would you ever see cosine of sine of t? But I'll show you how that can kind of be more useful later on. So when we check in the derivative of this, so f prime, we'll need to take g prime of t times f prime of g of t. And the way we can kind of think about this, it's easier to view in the fractional way that we were looking at. So the df dt is, we can say df dt is equal to df dg times dg dt. And you can think of it as the dg's canceling out. That's not what's really happening, but it's a notational trick that just happens to work out. So yeah, that's how we need to calculate the derivative in this way. So we take the derivative of f, so this entire thing with respect to g, so treating g as if it were a function or a variable in itself, and then taking the derivative of the inner, so the inner function g, and multiplying them two. So when we are taking this example here, we'll say the derivative of cosine with respect to this g of t here. So we can evaluate, we know that f of t here is going to be cosine of t, and g of t is sine of t. Because when we slot this g of t in, we'll get the same thing that we have up here. So we need to get f prime of t. The derivative of a cosine function is the minus the sine function. This is just something that kind of works out, not too important of how we got there. But there are a group of functions like cosine, sine, so general trig functions, the exponential function, logarithmic function. That's just kind of a good idea to have in your head already. These are all derived from first principles, but having them to stick in your head to remember is quite useful. So we have f prime of t, and we have g prime. So g prime of t, derivative of the sine function, is the cosine function. And now we just need to fit this back into our equation from up here. So f prime of t is minus sine of t, but we have to evaluate, sorry, g prime of t is cosine of t, and then we have f prime of t is minus sine of t, but we're going to have to remember to evaluate this instead of at t, at g of t. So we have that times minus sine of g of t, which is sine of t. So that means our entire derivative will be minus cos of t times sine of t. This gets a lot more useful when you think of it like the likes of exponential functions where you have, say, some e to the f of t, where you want to take a derivative of that, which is quite useful in the likes of differential equations. Or these are all quite important tools that now, together, we have really everything we'll need to take any derivative that comes our way. So yeah, that's pretty much everything you'll need to know about single variable differential calculus.